Subscribe to the channel so you don't miss out on any of these videos. Imagine staring up at the night sky, filled with a sea of stars. What if I told you that what we can see is just the tip of the iceberg? There's an invisible veil that surrounds every galaxy, an unseen halo of hot gas that we've only recently started to understand. These massive, almost ghostly envelopes of gas, called Galactic Coronae, play a crucial role in how galaxies evolve, how they interact with their environment, and even how the stars within them live and die. But for a long time, they've been hidden, eluding detection in ways that have left scientists puzzled. Galactic Coronae are not just some distant, abstract concept either. They're a key piece of the cosmic puzzle, and their discovery has been one of the most exciting breakthroughs in modern astronomy. These hot gas halos are massive, often millions of light years across, and they're extremely hard to study. Yet, they're crucial to understanding the fundamental workings of galaxies and the larger forces at play in the universe. When we think of a galaxy, we usually picture the bright, dense disk of stars, planets, and nebulae that we can see through telescopes. But beyond that disk, there's a vast, invisible region of gas that is just as important. This gas is hot, incredibly diffuse, and surrounds the galaxy like a ghostly halo. For decades, scientists couldn't see it. It was there, but it was hidden, a part of the galaxy's structure that went unnoticed by traditional methods of observation. However, advancements in technology, particularly with space telescopes and X-ray observations, have started to peel back the layers of this mystery. A galactic corona is a vast reservoir of hot gas, often heated to millions of degrees, that extends far beyond the visible galaxy. This gas is part of the galaxy's extended halo, a region of space where dark matter, gas, and even stars are present, though the stars are often so faint and scattered that they don't make much of an impact. It's in these coronae that we begin to see the true scale of a galaxy, far beyond what's visible with our eyes. But what exactly are these gas halos made of? Well, they're primarily composed of plasma, a hot, electrically charged gas that is a key component of the universe at large. This plasma is so hot that it emits X-rays, which is how we've been able to detect it. The gas that makes up these coronae is not uniform either. It has a complex structure, with varying densities and temperatures, and it's constantly interacting with the galaxy's environment. The gas in the corona can be influenced by the galaxy's gravitational pull, the movement of stars, and even the flow of gas into and out of the galaxy. These coronae are not just there to fill space. They have a very real impact on the life of the galaxy. One of the most important roles they play is in regulating the galaxy's star formation. The hot gas in the corona can heat up and regulate the cooling of gas within the galaxy's disk. This cooling process is essential for star formation, as cooler gas condenses to form new stars. Without this regulation, the galaxy could either run out of fuel for star formation too quickly or never form stars at all. But that's not all. These gas halos can also influence the galaxy's overall dynamics. They play a role in how the galaxy interacts with its surrounding environment. Galaxies don't exist in isolation. They're part of larger cosmic structures like galaxy clusters, and these clusters exert a huge amount of gravitational influence on the galaxies within them. The gas in the corona acts as a buffer, helping to shield the galaxy from some of the external forces acting on it. It can also interact with the intergalactic medium, the vast expanse of gas that exists between galaxies. These interactions can influence the galaxy's shape, its rotation, and even how it evolves over time. So, how do scientists study these elusive coronae? It's not easy, that's for sure. Detecting these gas halos requires the use of advanced telescopes that can observe in wavelengths beyond visible light, particularly in the X-ray part of the spectrum. The gas in a galactic corona is so hot that it emits X-rays, which are detectable by space telescopes. However, the challenge lies in the fact that this gas is spread out over vast distances, making it difficult to pinpoint. It's not like the stars in a galaxy, which shine brightly and are easy to see. Instead, the gas in the corona is faint and spread thin, like the wisps of smoke rising from a fire, barely visible in the vast expanse of space. One of the most significant breakthroughs in our understanding of galactic coronae came from the Chandra X-ray Observatory, which has provided some of the clearest images of these hot gas halos. The data from Chandra has shown that these coronae are not only massive but also very dynamic. The gas is constantly moving, interacting with the galaxy and its surroundings in ways that we're only beginning to understand. Another key piece of the puzzle came from observations made with the Hubble Space Telescope, which has helped to map the distribution of gas in and around galaxies. Using a technique called absorption spectroscopy, scientists have been able to study the light passing through these gas halos, which allows them to measure the gas's density, temperature, and composition. This has provided crucial insights into how the coronae are structured and how they interact with the galaxy's environment. As we continue to study these mysterious gas halos, we're beginning to uncover new and exciting possibilities. For example, some scientists speculate that the hot gas in the corona might actually be the result of supermassive black holes at the center of galaxies. These black holes are capable of creating vast amounts of energy, and that energy could be driving the formation of these gas halos. This idea is still being explored, but it's one of many exciting avenues of research that could lead to even more groundbreaking discoveries. One of the most intriguing aspects of galactic coronae is their potential to answer some of the biggest questions about the evolution of galaxies. The hot gas in these coronae is thought to be closely tied to the processes that govern the growth and formation of galaxies. By studying these gas halos, we can learn more about how galaxies form, how they interact with their environments, and how they evolve over time. The study of galactic coronae is still in its early stages, but the discoveries that have been made so far are both surprising and enlightening. We now know that these gas halos are not just passive regions of space. They are active, dynamic components of the galaxy, influencing everything from star formation to the galaxy's overall structure. In many ways, they are the unseen engines that drive the evolution of galaxies, helping to regulate the birth and death of stars, the flow of gas, and the interactions with other galaxies. The future of galactic corona research looks bright. With new advancements in telescope technology and improved observational techniques, we're poised to learn even more about these fascinating structures. As we continue to explore the universe, it's clear that galactic coronae will play a key role in our understanding of the cosmos. As the study of galactic coronae deepens, the more we begin to understand their importance in the broader context of cosmic evolution. These hot gas halos are not just passive observers of galactic life, they actively shape the destiny of galaxies. One of the key factors in their influence is the way they interact with their galaxy's central supermassive black hole. These black holes, often at the heart of galaxies, are powerful engines that can generate immense amounts of energy. Their gravitational pull is so strong that it can influence everything around them, including the hot gas in the corona. It's believed that the hot gas found in the corona might be a product of the activity surrounding the supermassive black hole. As the black hole pulls in matter from the surrounding galaxy, some of this material doesn't get devoured immediately. Instead, it heats up, creating high-energy radiation and powerful outflows of gas, which may spread out to form the corona. This process is thought to play a key role in regulating the amount of gas that remains available for star formation in the galaxy's disk. However, this isn't just a one-way interaction. The corona itself can influence the behavior of the black hole. The gas within the halo can flow inward, feeding the supermassive black hole, and in turn, the black hole can expel matter back into the corona through powerful jets of energy. This dynamic exchange between the black hole and its surrounding corona is a delicate balance, and understanding how this works is a major focus of current research. There's also the matter of galactic winds. These winds are fast-moving streams of gas that are often driven by the intense radiation emitted by the central black hole, or by large-scale starbursts in the galaxy. These winds can blow outwards from the galaxy's center, disturbing the gas in the corona and even pushing some of it into intergalactic space. This process is important because it can significantly alter the mass and structure of a galaxy over time. By studying these winds and their interaction with the corona, scientists can gain insights into how galaxies evolve and how they shed or retain gas throughout their lifespan. Another key aspect of galactic coronae is their role in the overall balance of energy in a galaxy. As galaxies form and grow, they undergo a complex cycle of gas accretion, star formation, and supernova explosions. The hot gas in the corona plays a critical role in regulating this cycle by absorbing and redistributing energy. For example, the corona can act as a kind of heat reservoir, absorbing the excess energy produced by star formation and preventing it from disrupting the galaxy's internal structure. This energy regulation helps to maintain a stable environment within the galaxy, allowing stars to form at a steady pace and preventing the galaxy from running out of the necessary raw materials for future generations of stars. But galactic coronae are not limited to just one type of galaxy. While they're often associated with large spiral galaxies like the Milky Way, they can also be found around smaller galaxies, and even in the halos of elliptical galaxies. The structure and size of these coronae can vary depending on the type of galaxy they surround. For example, the corona around an elliptical galaxy might be much more diffuse and spread out, while the corona around a spiral galaxy could be denser and more compact. These differences provide astronomers with valuable clues about how galaxies form and evolve in different environments. As we continue to gather more data, we're also beginning to see just how common galactic coronae are across the universe. Early studies suggest that virtually all galaxies are surrounded by some form of hot gas halo, though the characteristics of these halos can vary widely. This raises the possibility that galactic coronae are not just a curiosity, but an essential component of galaxy formation and evolution. They could be key to understanding the life cycle of galaxies and the mechanisms that drive their growth and development. While our understanding of galactic coronae has come a long way in recent years, there's still much to learn. For example, one of the biggest mysteries surrounding these hot gas halos is how they interact with dark matter. Dark matter, the invisible substance that makes up a large portion of the universe's mass, has a huge impact on the structure of galaxies. The gas in the corona might be interacting with dark matter in ways that we don't yet fully understand. Some theories suggest that dark matter could be influencing the way the gas is distributed or even heating it up, though this is still speculative. Another mystery is the origin of the hot gas in the corona. While we know that some of this gas is likely produced by the central black hole, there's still debate about how much of it comes from the galaxy's own star formation activity, and how much comes from interactions with other galaxies. Galaxies are constantly colliding and merging with one another, and these interactions can trigger the release of massive amounts of gas. Understanding how these galactic mergers influence the corona will help scientists build a more complete picture of the life cycle of galaxies. One of the most fascinating aspects of galactic coronae is their potential to provide insights into the early universe. Because these gas halos are so large and diffuse, they can act as a kind of cosmic archive, preserving information about the conditions that existed in the early stages of galaxy formation. By studying the gas in the corona, scientists can learn about the processes that led to the formation of the first galaxies, stars, and even the very elements that make up everything we see around us. This research could help to answer some of the most profound questions about the origins of the universe and the nature of cosmic evolution. As we look to the future of galactic corona research, there are several exciting developments on the horizon. The next generation of space telescopes, such as the James Webb Space Telescope, is expected to provide even more detailed observations of these hot gas halos. With its advanced instruments and ability to observe in infrared wavelengths, the James Webb Space Telescope will give scientists an unprecedented view of galactic coronae, allowing them to probe deeper into the structure of these mysterious halos and uncover new insights into the forces shaping galaxies. In addition, upcoming missions such as the Athena X-ray Observatory are specifically designed to study the X-ray emissions from hot gas halos. These missions will provide even more detailed maps of the gas in the corona, allowing scientists to study its temperature, density, and chemical composition with unprecedented precision. This will help to refine our understanding of how these gas halos are structured and how they evolve over time. With each new discovery, the role of galactic coronae in the larger framework of galactic dynamics becomes clearer. We're now seeing that these hot gas halos are much more than just a backdrop to the visible galaxy. They're active, dynamic components that influence everything from star formation to the behavior of supermassive black holes. The research into galactic coronae is one of the most exciting and promising areas in modern astronomy, And as we continue to explore these mysterious structures, we're sure to uncover even more revelations about the fundamental processes that govern our universe. As we continue to delve into the study of galactic coronae, we begin to realize that these halos are not only critical for understanding the present-day behavior of galaxies, but also provide important clues about their past and future. Observing how gas behaves in these coronae is like looking at a snapshot of the galaxy's evolutionary journey. The way it interacts with its central black hole, how it's affected by cosmic events like supernovae, and how it may be influencing the environment around it all speak to a galaxy's developmental history. Galactic coronae can also help us understand the broader workings of the universe. They act as a bridge between smaller-scale phenomena, like star formation, and large-scale cosmic events, like galaxy mergers. It's thought that the dynamics within the corona can offer vital clues about the large-scale flow of gas throughout the universe. For example, when galaxies collide, the behavior of their coronae can tell us how material is exchanged and redistributed across vast distances. These exchanges play a crucial role in galactic evolution, fueling new generations of stars and helping shape the structure of the universe as a whole. In many ways, studying these gas halos is akin to investigating the skeleton of the universe. While the visible matter, the stars and the nebulae, takes the spotlight, the gas in the corona, invisible to the naked eye, provides the framework for everything else. Without this halo, galaxies would not have the resources they need to sustain their growth, and the balance between star formation and the consumption of gas would be disrupted. Even the study of galaxy formation itself can benefit from a deeper understanding of galactic coronae. In the early stages of galaxy formation, it's believed that galaxies initially develop a significant amount of gas within their corona. This gas acts as a reservoir, one that can be tapped for star formation. However, as the galaxy matures, this gas can be depleted through processes like star formation and black hole accretion. Understanding how the gas in the corona is replenished, and how it gets lost over time, is vital to understanding how galaxies evolve through the cosmic ages. There's also the intriguing question of whether galactic coronae can help explain the mysterious dark matter that seems to make up the majority of the universe's mass. While dark matter has never been directly observed, its effects are seen in the way galaxies rotate and in the gravitational pull they exert on surrounding matter. The corona, being a large and diffuse structure, might provide a unique lens through which to study the relationship between visible gas and dark matter. Some scientists hypothesize that dark matter could be interacting with the gas in the corona in ways that we don't yet fully understand. This could offer important new insights into one of the most significant and perplexing phenomena in modern physics. On a more cosmic scale, galactic coronae might hold clues to understanding the overall life cycle of galaxies. As galaxies continue to evolve, their gas halos change in response to a variety of internal and external factors. The heat, density, and chemical makeup of the gas in the corona are all influenced by the galaxy's ongoing activities, like star formation and black hole accretion, as well as interactions with nearby galaxies. These changes could ultimately determine a galaxy's fate, whether it will continue to form stars, slowly fade into a passive state, or possibly be consumed by a neighboring galaxy in a merger. One fascinating aspect of these halos is their relationship with active galactic nuclei, AGNs. AGNs are extremely bright and energetic regions found at the center of some galaxies, powered by the accretion of matter onto a supermassive black hole. These black holes release enormous amounts of energy as they feed on surrounding gas, and that energy can directly influence the gas in the corona. It is believed that AGNs may drive outflows of hot gas into the surrounding corona, and in turn, these outflows could have a profound effect on the evolution of the galaxy. The study of this relationship could eventually help us understand how galaxies interact with the high-energy environments around them, and how they remain alive and dynamic over billions of years. But while much of our focus has been on the role of the corona in regulating star formation and interacting with black holes, there's another layer to consider: the corona's influence on galaxy clusters. A galaxy cluster is a massive collection of galaxies bound together by gravity, and many of these clusters contain vast reservoirs of hot gas known as the intracluster medium, ICM. The gas in the corona of individual galaxies interacts with this larger-scale cosmic structure, affecting how galaxies within the cluster behave. The cooling and heating of gas in these regions is thought to play a central role in determining the overall structure and evolution of galaxy clusters. In fact, many of the phenomena we observe in galaxy clusters, such as the formation of supermassive black holes or the creation of new stars, might be heavily influenced by the gas in the corona and its interactions with the ICM. Moreover, studying the behavior of galactic coronae in galaxy clusters opens up intriguing possibilities for future research. If we can observe the way gas flows between galaxies within a cluster, we may uncover new insights into the interactions between galaxies and how they form and grow in these dense environments. This could lead to breakthroughs in our understanding of how the universe's most massive and influential structures evolve. A particularly exciting prospect on the horizon is the potential to directly observe the gas in galactic coronae with the next generation of telescopes and observatories. Instruments like the James Webb Space Telescope and the Athena X-ray Observatory, both of which are equipped to study high-energy phenomena, are expected to offer unprecedented views of the hot gas in these halos. With these tools, astronomers will be able to observe the corona in greater detail than ever before. We may soon be able to map out the temperature, density, and chemical composition of the gas, offering clues about the processes taking place within and around the halos. Moreover, new computational techniques are allowing scientists to create more accurate simulations of galactic coronae. These models are incredibly sophisticated, accounting for a range of variables such as the movement of gas, the influence of the black hole, and the effects of cosmic radiation. By comparing these models to real observational data, astronomers can test different theories about the formation, evolution, and role of these hot gas halos. Such simulations are not only helping to solve the mysteries of the coronae themselves but are also shedding light on the broader processes governing galactic evolution. As our understanding of galactic coronae continues to grow, it's becoming clear that these mysterious halos play a far more significant role in the life of a galaxy than we ever imagined. From regulating star formation to influencing the dynamics of black holes and galaxy clusters, the gas in the corona is a vital piece of the cosmic puzzle. Understanding its properties and interactions will give us a deeper insight into the forces shaping galaxies and may ultimately help us unravel some of the greatest mysteries of the universe. As our tools and techniques for exploring galactic coronae become more advanced, one of the most exciting developments is the possibility of tracing the evolutionary timeline of these halos. By looking at the gas content of a galaxy's corona, astronomers can determine a great deal about the galaxy's past. For example, if a galaxy's corona shows signs of having been heated up by energetic processes, such as a starburst or a nearby supernova explosion, it suggests a period of intense activity. Conversely, if a galaxy's corona is cooler and more stable, it might indicate a more passive phase in its history. This is significant because it allows scientists to reconstruct a galaxy's developmental milestones, from its earliest stages of formation to the present-day structure we observe. In particular, studying the gas content of a galaxy's corona can reveal information about the processes that shaped it early on. For instance, galaxies that formed within the first few billion years of the universe's existence likely had very different gas distributions compared to more mature galaxies. This difference is important because the amount of gas available in a galaxy's halo determines its ability to form stars, and therefore, its overall evolution. A rich gas halo means a higher potential for star formation, while a depleted one could lead to a more passive galaxy, one that has exhausted its resources for new star birth. Interestingly, the study of galactic coronae may also provide clues about the role of cosmic filaments in galaxy formation. Cosmic filaments are vast structures of dark matter and gas that connect clusters of galaxies across the universe. These structures act as highways for the flow of gas and other materials, and they are thought to play an important role in galaxy formation. The interaction between galactic coronae and these cosmic filaments could offer further insight into the dynamics of galaxy assembly on the largest scales. By studying how galaxies accrete gas from these cosmic filaments and how this affects the properties of their coronae, scientists could learn more about the mechanisms that govern the growth and evolution of galaxies. This concept of galactic gas flow is particularly intriguing when we consider how galaxies may evolve in isolation versus in groups. In isolated galaxies, the gas within the corona is primarily influenced by internal processes, such as the movement of stars, the activity of the central black hole, or supernova explosions. But in a galactic cluster, the gas in the corona is influenced by the environment. The corona gas is constantly interacting with the intracluster medium, ICM, and in some cases, it may even be stripped away by the pressure exerted by the hot gas within the cluster. This stripping, known as ram pressure stripping, can significantly affect the evolution of a galaxy's gas content, leading to changes in its star-forming potential and overall structure. The effects of such interactions are far-reaching. When a galaxy loses its gas to the intracluster medium, it may experience a decline in star formation, a phenomenon known as starvation. This could lead to the galaxy transitioning into a passive state, ceasing to form new stars as it runs out of the fuel it needs. On the other hand, if a galaxy retains its gas or continues to accrete gas from the surrounding environment, it can remain an active site of star formation for much longer, contributing to the overall evolution of its cosmic neighborhood. In the case of galaxies at the center of clusters, the interplay between their corona and the surrounding gas is even more pronounced. Some of these central galaxies are surrounded by vast halos of gas, which are enriched by material from other galaxies. These central galaxies play a pivotal role in the cluster's evolution, as they are often the largest and most influential members. Their coronae can have a significant impact on the rest of the cluster, either by injecting energy and gas into the surrounding environment, or by serving as a reservoir that helps regulate the dynamics of the entire cluster. As we peer deeper into the mysteries of galactic coronae, one of the more recent developments in this field is the study of feedback mechanisms. Feedback refers to the process by which a galaxy's activity influences its own growth and the surrounding environment. In the case of coronae, feedback occurs when energy from supernovae, black hole accretion, or star formation is transferred to the surrounding gas. This energy can either heat the gas, preventing it from cooling and condensing into new stars, or it can drive powerful outflows that eject gas from the galaxy entirely. Feedback mechanisms are central to understanding why some galaxies continue to form stars at a high rate, while others shut down. For example, in galaxies with powerful active galactic nuclei, AGNs, the energy emitted by the central black hole can heat up the gas in the corona, preventing it from cooling and collapsing into new stars. This process, known as AGN feedback, is thought to be a major factor in regulating star formation in massive galaxies. Without this feedback, galaxies might continue to form stars at an unsustainable rate, ultimately depleting their gas and evolving into red and dead galaxies, passive systems that no longer form stars. But the role of feedback doesn't end with AGNs. Supernova explosions, too, can play a role in regulating the gas in a galaxy's corona. When a star explodes as a supernova, it releases vast amounts of energy that can heat and expel gas from the galaxy. This process, known as supernova feedback, can both enrich the gas in the corona with heavier elements and remove excess gas that would otherwise have contributed to further star formation. The balance between AGN feedback and supernova feedback is thought to be crucial in determining a galaxy's ability to form new stars over time. On the flip side, we also have to consider how galaxies replenish their gas. While internal processes such as supernovae and AGNs can strip away gas, galaxies can also accrete new gas from their environment. For example, in regions with abundant cosmic filaments, gas from the intergalactic medium can flow into a galaxy's corona, replenishing its gas supply and potentially triggering new star formation. This process of accretion is particularly important for galaxies in the early stages of formation, when they are still building up their mass and resources. The way in which a galaxy accretes gas, and how it interacts with the gas in its corona, can have lasting effects on its overall evolution. For instance, galaxies that are able to efficiently accrete gas are often more successful in sustaining star formation for longer periods of time. In contrast, galaxies that lose more gas through feedback or stripping processes may be more likely to become passive over time. This is one reason why studying the dynamics of galactic coronae is so crucial. It allows us to understand the delicate balance between star formation, gas accretion, and feedback, which ultimately dictates the fate of a galaxy. As we look to the future of galactic corona research, one of the most exciting prospects is the ability to directly observe these halos in unprecedented detail. With the advent of advanced space telescopes, such as the James Webb Space Telescope, and upcoming missions like the Athena X-ray Observatory, astronomers are poised to make groundbreaking discoveries about the hot gas that surrounds galaxies. These tools will allow scientists to map the gas and galactic coronae with greater precision, uncovering new insights about the way galaxies form, evolve, and interact with their environments. The study of galactic coronae is still in its early stages, but it has already revealed a wealth of information about the complex and dynamic nature of galaxies. As we continue to observe and model these halos of hot gas, we will unlock even more secrets about the forces that shape the universe. From understanding the fate of individual galaxies to unraveling the mysteries of large-scale cosmic structures, galactic coronae are poised to remain at the forefront of astronomical research for many years to come. As we continue to dive deeper into the study of galactic coronae, it is becoming increasingly clear that these vast, invisible halos of hot gas are not just passive bystanders in the grand scheme of galactic evolution. In fact, they play a central role in shaping the future of galaxies and influencing the larger-scale structure of the universe. This growing understanding of galactic coronae challenges many of the assumptions we once held about galaxy formation, and it has profound implications for our understanding of the cosmos as a whole. One of the key insights emerging from recent research is the idea that galactic coronae are not static entities, but rather highly dynamic structures. Over time, they undergo significant changes, driven by a variety of processes, including feedback from stars and black holes, interactions with the intergalactic medium, and the accretion of gas from cosmic filaments. These changes can have far-reaching consequences for the galaxy itself, affecting everything from its star formation rate to its long-term survival. For example, in some cases, the gas in a galaxy's corona may become so hot and diffuse that it no longer supports active star formation. Instead, the galaxy transitions into a red and dead state, characterized by a lack of new stars and a gradual fading of its existing stellar population. This process, known as quenching, is thought to be closely tied to the behavior of the galaxy's corona. In these cases, the feedback mechanisms within the corona, such as AGN and supernova feedback, become so strong that they prevent the cooling of gas, halting the process of star formation altogether. However, this is not the only path that a galaxy can take. For galaxies that retain a steady supply of gas through accretion from the intergalactic medium or cosmic filaments, the future can look very different. These galaxies are able to continue forming stars at a high rate, maintaining their vibrancy and growth over billions of years. The interaction between a galaxy's corona and its environment becomes a key factor in determining whether the galaxy will thrive or fade away. In this sense, the galactic corona serves as a barometer for the health and vitality of the galaxy, offering clues about its potential for future growth and evolution. One particularly intriguing aspect of this dynamic is the relationship between galactic coronae and the large-scale structure of the universe. As we mentioned earlier, cosmic filaments, vast stretches of dark matter and gas that connect galaxies, play a crucial role in shaping the formation and evolution of galaxies. These filaments are the highways through which gas flows into galaxies, providing the fuel for star formation and driving the growth of the galaxy's corona. The interaction between a galaxy's corona and these cosmic filaments is a fascinating area of study, as it holds the key to understanding how galaxies grow and evolve within the broader framework of the universe's large-scale structure. In particular, the way in which gas flows from the intergalactic medium into a galaxy's corona can have profound effects on the galaxy's star formation history. Galaxies that are located near cosmic filaments are more likely to have access to a steady stream of gas, which allows them to continue forming stars over long periods of time. In contrast, galaxies that are isolated or located in regions with little access to cosmic filaments may struggle to replenish their gas supplies, leading to a cessation of star formation and a gradual fading of their stellar populations. This connection between galactic coronae and cosmic filaments highlights the intricate interplay between galaxies and their environments. It suggests that the fate of a galaxy is not determined solely by its internal processes, such as feedback from stars and black holes, but is also deeply influenced by the larger-scale cosmic web in which it is embedded. As a result, the study of galactic coronae is inseparable from the study of the universe's large-scale structure, offering a unique window into the interconnected nature of the cosmos. Another exciting avenue of research is the potential for galactic coronae to shed light on the nature of dark matter, one of the biggest mysteries in modern physics. While dark matter cannot be directly observed, its presence is inferred through its gravitational effects on visible matter. Galactic coronae, particularly the hot gas in their halos, may offer indirect evidence for the existence of dark matter. The way in which galaxies interact with their coronae, and the way in which gas flows through these halos, could provide important clues about the distribution and properties of dark matter in the universe. For example, the presence of dark matter may influence the distribution of gas in a galaxy's corona. Dark matter, which is thought to be spread throughout the universe in large halos, could exert a gravitational pull on the surrounding gas, shaping the structure of the corona and influencing its behavior. By studying the way in which gas interacts with dark matter in the context of galactic coronae, scientists may be able to glean new insights into the properties of dark matter, including its mass, distribution, and role in galaxy formation. This connection between galactic coronae and dark matter is still an area of active research, but it represents one of the most exciting possibilities for the future of cosmology. As new observational techniques and technologies become available, such as the next-generation X-ray observatories and advanced simulations, scientists will be able to probe deeper into the mysteries of dark matter and its relationship to the hot gas and galactic coronae. These breakthroughs could potentially revolutionize our understanding of both the nature of dark matter and the process of galaxy formation itself. Of course, it's important to recognize that our current understanding of galactic coronae is still in its infancy. While we have made great strides in uncovering the properties and dynamics of these hot gas halos, there is still much that we don't know. For example, we have yet to fully understand the role that magnetic fields play in shaping the behavior of gas in the corona. Magnetic fields are known to exist in many astrophysical environments, and they could have a significant impact on the dynamics of the gas within galactic coronae. However, the precise nature of these magnetic fields, and their influence on the gas, remains an open question. Additionally, the exact relationship between galactic coronae and the formation of supermassive black holes is still a subject of intense debate. While we know that supermassive black holes reside at the centers of most galaxies, the precise role they play in shaping the properties of the galaxy's corona is still not fully understood. Some researchers speculate that the presence of a black hole could directly influence the gas in the corona, either by heating it through accretion or by driving powerful outflows that shape the gas distribution. Others suggest that the relationship between black holes and galactic coronae may be more indirect, with black hole activity influencing the overall dynamics of the galaxy in a broader sense. The study of galactic coronae is also complicated by the fact that these structures are often difficult to observe directly. Because the gas in these halos is extremely diffuse and faint, it can be challenging to detect with current observational techniques. However, advances in observational technology, such as the use of X-ray telescopes and high-resolution simulations, are beginning to overcome these challenges. As our tools for studying galactic coronae continue to improve, we can expect to uncover even more about these hidden structures and their role in shaping the universe. As we look to the future of galactic corona research, it's clear that these mysterious halos of hot gas will continue to be a key focus of scientific inquiry. From shedding light on the evolution of galaxies to providing clues about the nature of dark matter, the study of galactic coronae promises to reveal some of the most profound and fundamental aspects of the universe. By peering into these invisible halos, scientists are unlocking secrets that could transform our understanding of the cosmos and our place within it. As we continue to explore the complex and fascinating world of galactic coronae, it's important to recognize that their study is not just a theoretical exercise but one that is deeply intertwined with the future of observational astronomy. The mysteries they harbor are not just limited to their composition and role in galactic dynamics but also to their potential to provide insight into some of the most fundamental questions in astrophysics. With new technologies coming online and more ambitious missions planned for the coming decades, the answers to these questions may be closer than we think. One area where significant progress is being made is in the development of observational techniques specifically designed to probe the hot, diffuse gas that makes up a galactic corona. This gas, often in the form of a plasma, is extremely faint and hard to detect with traditional optical telescopes. However, the advancement of X-ray astronomy has provided a powerful tool to explore these elusive halos. X-ray telescopes, such as the Chandra X-ray Observatory and the upcoming James Webb Space Telescope, JWST, have revolutionized our ability to observe the high-energy processes occurring in these distant regions of space. X-ray observations are particularly important because the gas in galactic coronae is often heated to temperatures of millions of degrees, making it emit X-rays that are detectable by space-based telescopes. This allows astronomers to study the composition, temperature, and density of the gas in these halos, as well as to map their distribution around galaxies. X-ray observations also provide insights into the energetic processes taking place within these coronae, including the influence of active galactic nuclei, AGN, supernovae, and cosmic rays. The ability to observe galactic coronae in X-rays is not only important for understanding their structure and behavior but also for probing the large-scale environment in which galaxies reside. These halos of hot gas extend well beyond the visible boundaries of the galaxy itself, and by studying their interactions with the surrounding intergalactic medium, scientists can gain a clearer picture of the overall dynamics of the galaxy and its role in the cosmic web. This is particularly valuable for understanding the processes of galaxy formation and evolution, as the interplay between the gas in the corona and the larger-scale environment has profound implications for the growth and fate of galaxies. One of the challenges that astronomers face in studying galactic coronae is the fact that these halos often extend to great distances from the galaxy's core, making them difficult to observe with the precision required to fully understand their structure. This is where advanced simulations come into play. The use of high-resolution computational models is allowing scientists to simulate the behavior of gas in galactic coronae with greater accuracy than ever before. These simulations take into account a wide range of physical processes, from gravitational interactions to magnetic fields, and provide detailed predictions that can be tested against observational data. One particularly exciting development in this area is the use of simulations to study the interactions between galactic coronae and the cosmic filaments that connect galaxies across vast distances. These simulations have revealed that the inflow of gas from these cosmic structures plays a crucial role in the formation and growth of a galaxy's corona. In some cases, the interaction between the gas in the corona and the cosmic filaments can trigger the cooling of the gas, leading to the formation of new stars. In other cases, the inflow of gas can be halted or disrupted by processes such as shock waves or feedback from AGN, preventing further star formation and leading to the quenching of the galaxy. By combining observational data with high-resolution simulations, scientists are beginning to piece together a more complete picture of how galactic coronae evolve over time and how they interact with their larger cosmic environment. These advances in our understanding are helping to refine our models of galaxy formation and are providing new insights into the complex processes that drive the evolution of the universe itself. In addition to the role of cosmic filaments, researchers are also exploring the potential connection between galactic coronae and the phenomenon known as feedback. In the context of galactic evolution, feedback refers to the processes by which energy and matter are exchanged between a galaxy's central black hole, its stars, and the surrounding gas. Feedback mechanisms, such as those triggered by supernovae or AGN activity, can have a profound impact on the evolution of a galaxy's corona, influencing everything from the temperature and density of the gas to the rate of star formation. One of the most striking examples of feedback in action is the influence of active galactic nuclei, AGN, on the gas in a galaxy's corona. AGN are thought to be powered by supermassive black holes at the centers of galaxies, and they release vast amounts of energy in the form of radiation and particle jets. This energy can have a profound effect on the surrounding gas, heating it to extremely high temperatures and driving powerful outflows of gas away from the galaxy. These outflows, known as AGN winds, can have a dramatic impact on the gas in the corona, potentially preventing it from cooling and collapsing to form new stars. In some cases, AGN feedback can even be responsible for quenching star formation in a galaxy. By heating the gas in the corona to such high temperatures, AGN can prevent the gas from cooling and condensing into dense clouds, which are the precursors to new stars. This process can lead to a situation where a galaxy ceases to form new stars and gradually fades into a red and dead state. Understanding the role of AGN feedback in shaping galactic coronae is a key area of research, as it provides important clues about the long-term evolution of galaxies and their ability to sustain star formation. In addition to AGN feedback, supernovae are another important source of feedback in galaxies. When massive stars reach the end of their lives and explode as supernovae, they release enormous amounts of energy, which can shock heat the surrounding gas and create powerful outflows. These supernovae-driven winds can have a similar effect on the gas in a galaxy's corona as AGN feedback, dispersing the gas and preventing it from cooling and forming new stars. The combined effects of AGN and supernova feedback are thought to play a central role in regulating the rate of star formation in galaxies, and they may be the key to understanding why some galaxies continue to form stars at a high rate, while others experience a dramatic decline in star formation activity. By studying the ways in which feedback processes influence galactic coronae, scientists hope to gain a deeper understanding of the factors that govern galaxy evolution and the processes that shape the life cycles of galaxies. As we look ahead to the next decade of astronomical research, it's clear that the study of galactic coronae will continue to be one of the most exciting and dynamic fields in astrophysics. With advancements in observational technology, such as the upcoming X-ray missions and the development of more sophisticated simulations, we are on the cusp of unlocking some of the deepest mysteries of the universe. These hidden halos of hot gas hold the key to understanding not only the evolution of galaxies but also the larger-scale structure of the cosmos, and the fundamental processes that govern the formation and growth of cosmic structures. The study of galactic coronae is more than just an exploration of distant galaxies and their gas halos. It is a journey into the very heart of the universe itself. By unraveling the mysteries of these elusive structures, we are not only gaining insight into the life cycles of galaxies but also discovering new ways to understand the vast, interconnected web of the cosmos. As we continue to push the boundaries of our knowledge, we can be sure that the hidden halos of hot gas surrounding galaxies will remain one of the most intriguing and enigmatic areas of study in the quest to understand the universe. As our understanding of galactic coronae deepens, one crucial aspect we have yet to fully grasp is their potential role in the larger cosmic cycle. These enormous halos of hot gas may act as essential components in the recycling of matter within the universe. The gas in these halos doesn't just sit idly around galaxies, but can also participate in a continual cycle of inflow and outflow. This cyclical process is thought to be responsible for regulating the birth and death of stars within galaxies, as well as shaping the ultimate fate of the galaxy itself. This cycle involves several key processes that are not yet completely understood, but astronomers are working tirelessly to piece them together. One possibility is that gas from the intergalactic medium, IgM, flows into a galaxy's corona, where it is heated up to incredibly high temperatures. This heated gas can then either be ejected back into the intergalactic space by powerful processes like supernovae or active galactic nuclei, AGN, or it can cool and fall back down toward the galaxy, enriching the galaxy with fresh material for star formation. This inflow and outflow of gas, often called galactic feedback, plays a crucial role in determining a galaxy's ability to sustain star formation over time. However, this process isn't simple, nor is it entirely predictable. The gas in the corona doesn't always behave in a straightforward manner. Depending on the factors influencing the galaxy, whether it's an influx of gas from the cosmic web, an energetic event such as a supernova, or the feedback from an AGN, this gas can either condense into new stars or be pushed back out into the broader universe. In fact, This interplay between the gas in the corona and the galaxy's core may help explain why some galaxies are star-forming, producing new stars at a rapid pace, while others are quenched, no longer forming stars. One fascinating aspect of this cycle is the role of the supermassive black holes found at the center of most galaxies. These black holes have an immense impact on their surroundings, not just due to their gravitational pull but because of the energetic feedback they produce. The matter falling into a black hole can produce high-energy jets and radiation that can affect the gas in the galactic corona. These outflows can prevent the gas from cooling, hindering star formation and slowing the overall growth of the galaxy. This phenomenon, called AGN feedback, is thought to be a significant factor in why some galaxies stop forming stars prematurely. AGN feedback can actually help explain some of the differences between massive, active galaxies and smaller, more passive ones. The intense radiation and energy produced by an AGN can heat the surrounding gas, preventing it from cooling and collapsing into dense molecular clouds, which are the building blocks for new stars. This suppression of star formation can have profound effects on a galaxy's evolution, as the absence of new stars leads to a gradual decline in the galaxy's brightness and activity. This feedback mechanism, along with others such as supernova-driven winds, plays a vital role in regulating the galaxy's evolution. But the story of Galactic Coronae doesn't just end with the dynamics of galaxies themselves. These massive halos of gas also interact with the larger-scale structure of the universe, specifically the cosmic web. The cosmic web is the vast network of interconnected galaxies, gas, and dark matter that forms the backbone of the universe. It's a structure that exists on scales much larger than individual galaxies, and it plays an integral role in the way galaxies evolve and interact with one another. Galactic coronae are not isolated systems but are part of this larger cosmic structure. The gas in these halos is not only influenced by the dynamics of the galaxy itself but also by the surrounding cosmic environment. For example, gas from the intergalactic medium, IgM, can flow into a galaxy's corona, enriching the galaxy with new material. Similarly, a galaxy's corona can lose gas to the surrounding cosmic web if it is unable to hold on to its gas due to energetic processes like AGN feedback or supernova winds. Interestingly, the cosmic web itself can also play a role in the distribution and composition of the gas in galactic coronae. Recent studies have suggested that the gas in the corona may be directly linked to the large-scale structure of the universe. This gas can be drawn into galaxies through cosmic filaments, which are long strands of dark matter and gas that connect galaxies across vast distances. These filaments are thought to be the primary channels through which galaxies receive their gas from the larger universe. The discovery that galactic coronae might be interconnected with the cosmic web has profound implications for our understanding of the universe. It suggests that the evolution of individual galaxies is not just a local process, but is deeply influenced by the larger-scale structure of the universe. By studying the way gas flows between galaxies, we can gain valuable insights into the mechanisms that drive galaxy formation and evolution on a cosmic scale. Another intriguing aspect of galactic coronae is the potential role they play in the formation of cosmic structures such as galaxy clusters. Galaxy clusters are enormous collections of galaxies, bound together by gravity, and they represent some of the largest structures in the universe. These clusters are filled with vast amounts of hot gas, known as the intracluster medium, ICM, which shares many similarities with the gas in galactic coronae. In fact, some researchers believe that the gas in a galaxy's corona might eventually become part of the ICM of a galaxy cluster. This connection between galactic coronae and galaxy clusters is still an area of active research, but it offers an exciting avenue for future investigations. If the gas from individual galactic coronae can indeed be incorporated into the ICM, it would suggest that the material in these halos is not just being cycled within individual galaxies but is instead being transported across large distances to become part of the larger structures of the universe. This could help to explain the distribution of gas in galaxy clusters and provide new insights into the formation and evolution of these massive cosmic structures. As we continue to refine our understanding of galactic coronae, it's clear that their study will have far-reaching implications for our understanding of the universe. These hidden halos of hot gas are not just fascinating objects in their own right, but they are also key pieces of the puzzle when it comes to understanding galaxy formation, evolution, and the large-scale structure of the universe. With advancements in observational technology and the development of more sophisticated simulations, we are on the cusp of unlocking some of the deepest mysteries of the cosmos. In the coming years, new missions and telescopes, such as the upcoming James Webb Space Telescope, JWST, and the next generation of X-ray observatories, will provide unprecedented opportunities to study galactic coronae in greater detail than ever before. These advancements promise to revolutionize our understanding of these mysterious gas halos and their role in shaping the universe. By continuing to explore these enigmatic structures, we may one day be able to answer some of the most fundamental questions in astrophysics and unlock the secrets of the cosmos. As we look to the future of galactic coronae research, one thing is certain: these invisible halos of hot gas will remain at the forefront of astrophysical inquiry. They are not just a curiosity in the sky, they are a vital part of the intricate web that connects galaxies, stars, and the larger universe. By studying galactic coronae, we are not only learning more about the life cycles of galaxies but also uncovering new ways to understand the vast and interconnected universe in which we live. To further understand the significance of galactic coronae, it's important to grasp the broader implications of their study. These gas halos are not only vital for understanding galaxy evolution but also for unraveling the mysteries of dark matter and dark energy, the two invisible forces that dominate the universe. Dark matter, which accounts for a significant portion of the universe's mass, does not interact with light, making it invisible to our current observational methods. Yet, its presence is inferred through its gravitational effects on galaxies, clusters, and the cosmic web. Galactic coronae, being closely linked to the larger structure of the universe, could offer indirect clues about dark matter's role in galaxy formation and its interaction with ordinary matter. One theory suggests that dark matter might play a crucial role in shaping the gas halos surrounding galaxies. Since dark matter is thought to be distributed in vast halos around galaxies and galaxy clusters, it may be influencing the movement and behavior of the gas in the corona. This would mean that the shape, size, and density of a galaxy's corona could be linked to the dark matter halo surrounding it. By studying the properties of galactic coronae, astronomers might be able to indirectly probe the distribution of dark matter within galaxies, helping to refine our models of its behavior and properties. This connection between dark matter and galactic coronae also ties into the broader question of how galaxies form and evolve over time. For many years, scientists have grappled with the question of how galaxies manage to hold on to their gas, preventing it from being stripped away by external forces. Some researchers hypothesize that dark matter plays a critical role in this process. If dark matter is indeed concentrated around galaxies in large halos, its gravitational influence could help keep the gas in the corona from being lost to the surrounding environment. This could explain why some galaxies are able to retain large amounts of gas in their halos, allowing for prolonged star formation and continued growth, while others, like the red and dead galaxies, may lose their gas and stop forming stars. In this context, studying galactic coronae could not only shed light on the evolution of individual galaxies, but also on the broader processes that govern galaxy formation. Understanding how gas behaves within these halos, and how it interacts with dark matter, could provide valuable insights into the forces that shape galaxies over cosmic time. The relationship between dark matter, gas, and galaxy dynamics is one of the most significant and challenging puzzles in modern astrophysics, and galactic coronae might hold the key to unlocking some of its mysteries. Another intriguing aspect of galactic coronae is their potential to help us understand the role of magnetism in the universe. Magnetic fields are thought to be pervasive throughout space, yet their origin and behavior are still not fully understood. Magnetic fields are found in stars, galaxies, and even the intergalactic medium, but their detailed structure and influence on galaxy evolution remain elusive. The gas in galactic coronae could provide an essential piece of the puzzle in understanding the cosmic role of magnetism. The interaction between magnetic fields and the hot gas in the corona could have profound effects on the dynamics of these halos. magnetic fields can influence the movement of charged particles within the gas, affecting the overall behavior of the gas in ways that are not yet fully understood. These interactions could also play a role in the way gas is heated or cooled within the corona. For example, magnetic fields may help channel energy from supernova explosions or AGN outflows, preventing the gas from cooling too quickly and allowing it to remain in the hot, ionized state necessary for the formation of a corona. Furthermore, magnetic fields could also be involved in the process of cosmic ray acceleration, which is thought to occur in the hot gas of galaxy clusters and supernova remnants. The connection between magnetic fields, cosmic rays, and galactic coronae could be an important area of future research, as it could reveal new insights into the processes that govern energy transfer in the universe. The study of galactic coronae is also critical for understanding the broader evolution of the universe itself. Galaxies, and by extension the gas in their coronae, play a central role in the large-scale structure of the cosmos. Galaxies are not isolated entities but are part of a much larger network of interconnected systems, known as the cosmic web. This web consists of vast filaments of dark matter and gas that stretch across billions of light-years, linking galaxies and clusters together. The gas in galactic coronae is intimately tied to this larger cosmic structure, as it is both a product of and a contributor to the evolution of the cosmic web. In fact, the interaction between galaxies and the cosmic web could help explain the formation of galaxy clusters. As gas flows from the cosmic web into the corona of a galaxy, it may contribute to the growth of the galaxy and the larger-scale structures around it. This process could also help explain the formation of superclusters, the massive clusters of galaxies that are among the largest structures in the universe. Understanding how gas moves through the cosmic web and into galactic coronae could provide critical insights into the formation of these gigantic cosmic structures. This understanding of galactic coronae as part of the larger cosmic structure also has implications for the study of cosmic evolution. Over time, galaxies grow and evolve through the accumulation of gas, the formation of stars, and the interactions with other galaxies and cosmic structures. The gas in galactic coronae plays a central role in this process, as it is the fuel for star formation and the primary means by which galaxies acquire the material they need to evolve. By studying the properties of this gas, astronomers can gain insights into the broader mechanisms that drive cosmic evolution, from the formation of galaxies to the growth of superclusters and beyond. Yet, despite all that we have learned, there is still much that remains a mystery about galactic coronae. One of the key questions that astronomers are still working to answer is how the gas in these halos behaves on very small scales. While we have made significant progress in understanding the large-scale dynamics of galactic coronae, we are still uncertain about the detailed processes that occur within them. How does the gas move within the corona? What are the physical processes that govern its temperature, density, and composition? And how does this gas interact with the galaxy's central supermassive black hole, stars, and other galactic structures? These are some of the questions that future research on galactic coronae will need to address. With the advent of next-generation telescopes and observatories, we are on the cusp of a new era of exploration. Instruments like the James Webb Space Telescope, the upcoming X-ray observatories, and powerful ground-based observatories will allow us to peer deeper into the heart of galaxies than ever before. These tools will provide us with new data on the temperature, composition, and dynamics of the gas in galactic coronae, helping to reveal the hidden secrets of these enigmatic structures. Moreover, as we continue to refine our understanding of the cosmic web and the interactions between galaxies, gas, and dark matter, we are likely to uncover new insights into the formation and evolution of galaxies on even larger scales. Galactic coronae are not just isolated systems but are part of the vast, interconnected web of matter that stretches across the universe. By studying these hidden halos of hot gas, we are not just learning about the life cycles of galaxies, but also about the larger processes that shape the universe itself. The study of galactic coronae is one of the most exciting frontiers in modern astrophysics. These mysterious halos of gas hold the key to understanding the evolution of galaxies, the nature of dark matter, and the dynamics of the cosmic web. As we continue to explore these hidden realms, we are bound to uncover new and unexpected discoveries that will reshape our understanding of the cosmos. As we venture deeper into the study of galactic coronae, it's crucial to consider the role of advanced computational models in enhancing our understanding of these elusive phenomena. Over the past few decades, simulations have become a key tool for astrophysicists trying to model the complex interactions within galaxy halos. These models are designed to replicate the dynamic processes that occur in galactic coronae, from the interplay between gas, dark matter, and magnetic fields, to the feedback mechanisms that regulate the flow of material in and out of galaxies. By utilizing advanced computational techniques, astronomers can simulate the behavior of gas at high resolution, incorporating factors such as temperature gradients, shock waves, and the effects of supernovae and active galactic nuclei, AGN. These simulations allow scientists to test different hypotheses about how galactic coronae form and evolve over time. They also provide insight into how gas might be stripped from galaxies, how it might cool or heat, and how it interacts with the surrounding intergalactic medium. In many ways, computational models are helping to bridge the gap between observation and theory. While we have made significant progress in understanding galactic coronae, many of the processes involved are too complex to observe directly with current technology. Simulations allow us to explore different scenarios and predict outcomes that can later be tested with new observational data. This iterative process of simulation and observation is one of the most powerful tools in modern astrophysics, and it will be instrumental in uncovering the secrets of galactic coronae. One of the most exciting prospects for the study of galactic coronae lies in the use of multi-wavelength observations. Different wavelengths of light, from radio waves to X-rays, reveal different aspects of the gas surrounding galaxies. X-ray observations, in particular, have been instrumental in detecting the hot, ionized gas that makes up the corona. Instruments like the Chandra X-ray Observatory and the upcoming Athena mission will provide unprecedented detail in mapping the temperature, density, and distribution of this gas. At the same time, radio and optical telescopes can be used to study the cooler components of the halo and the effects of feedback from stars and black holes. These multi-wavelength observations will not only allow us to map the structure of galactic coronae with greater precision, but also help us understand their relationship to the larger cosmic environment. For example, we might be able to study how gas flows into and out of galaxies, how it is affected by the gravitational pull of dark matter, and how it interacts with the intergalactic medium. These observations will provide a more holistic view of galaxy evolution, allowing us to connect the dynamics of the gas in the corona to the broader processes at play in the universe. In particular, the next-generation telescopes, such as the James Webb Space Telescope, will provide a wealth of data that could revolutionize our understanding of galactic coronae. Although Webb is primarily designed to study the infrared universe, its observations of distant galaxies will offer new insights into the processes that govern galaxy formation and evolution. By studying the light from galaxies that has traveled billions of years to reach us, we can observe them as they were in the early stages of their development. This will allow astronomers to investigate how galactic coronae form and evolve over time, shedding light on the conditions that lead to the creation of stars, black holes, and even entire galaxy clusters. However, to truly understand the role of galactic coronae in the cosmic landscape, we need to take a step back and consider the broader context of galaxy evolution. Galaxies are not static objects but are constantly changing, evolving, and interacting with their surroundings. The hot gas in a galaxy's corona is just one component of this dynamic process. The gas is constantly being replenished, heated, and lost to the surrounding environment, with the fate of the gas often determined by the complex interactions between the galaxy's dark matter, stars, and black hole. One of the key questions astronomers are asking is how the gas in the corona is connected to the life cycle of stars. Galaxies are continually forming new stars from the gas in their coronae. This star formation process is intimately linked to the cooling and heating mechanisms within the corona. If the gas cools too quickly, it will condense into dense regions that form stars. On the other hand, if the gas remains too hot, star formation may be suppressed. The balance between these processes is crucial for the evolution of the galaxy. If star formation is too vigorous, the gas in the corona can be depleted, leaving the galaxy with a sparse supply of raw material for new stars. If star formation is too slow, the galaxy may become quenched, no longer able to form new stars, and eventually fading into a red and dead state. Understanding how the gas in galactic coronae is regulated is one of the most important goals of current astrophysical research. This requires not only observing the gas itself but also understanding the feedback mechanisms that drive galaxy evolution. Active galactic nuclei, for example, can release vast amounts of energy into the surrounding gas, heating it up and preventing it from cooling and condensing into stars. Supernova explosions, too, can inject energy into the gas, both triggering star formation and disrupting the flow of material within the galaxy. The relationship between these feedback mechanisms and the hot gas in the corona is still not fully understood, but it is clear that they play a critical role in determining the fate of galaxies. Another key area of interest is the connection between galactic coronae and larger cosmic structures. As mentioned earlier, galaxies are part of the larger cosmic web, a vast network of filaments and voids that spans the entire universe. The gas in galactic coronae is connected to this web, with material flowing from the surrounding intergalactic medium into the halos of galaxies. This flow of gas can influence the rate of star formation and the growth of galaxies, with material from the cosmic web potentially being accreted into the corona to fuel new stars. Conversely, galaxies can also expel gas, sending it back into the cosmic web and influencing the formation of other galaxies. In this sense, the study of galactic coronae is not just about understanding individual galaxies, but also about exploring the interconnectedness of the universe. By studying these invisible halos of hot gas, astronomers can gain insights into the processes that shape the entire cosmic landscape, from the formation of galaxies to the growth of superclusters and beyond. The gas in the corona is both a product of and a contributor to the larger dynamics of the universe, and its study is essential for understanding the fundamental forces that govern the cosmos. With new technologies on the horizon and a growing body of observational data, we are entering a new era of discovery in the study of galactic coronae. The insights gained from these studies will not only deepen our understanding of galaxy formation and evolution but also provide critical clues about the nature of dark matter, dark energy, and the larger forces that shape the universe. As we continue to probe the mysteries of galactic coronae, we may be on the brink of discovering new and unexpected aspects of the cosmos, challenging our current models and expanding our knowledge of the universe in ways we never thought possible. As we continue to explore the mysteries of galactic coronae, the study of these enigmatic halos of hot gas presents us with a fascinating puzzle. One of the central questions is how galaxies can hold on to their gas, despite the immense forces acting on it. The balance between gravitational pull, the pressure of the hot gas, and the feedback from stars and black holes creates a delicate equilibrium. If the gas is too hot, it can escape the galaxy's gravitational pull, dissipating into the surrounding cosmic environment. But if it cools and condenses too quickly, it can trigger the collapse of new stars, leading to rapid galaxy evolution. The question, then, is how galaxies manage to maintain this balance over billions of years, allowing them to evolve in such a dynamic and diverse way. The nature of the feedback mechanisms at play within galactic coronae is another area of intense research. As mentioned, feedback from processes like supernovae and active galactic nuclei can have a profound effect on the gas in the corona. But these feedback mechanisms are not just limited to local events within a galaxy. They are part of a larger process of cosmic recycling, where gas flows between galaxies, clusters, and the intergalactic medium, constantly being exchanged and replenished. This cycle plays a key role in the distribution of gas across the universe and in the formation of structures like galaxy clusters and superclusters. Furthermore, the ongoing research into galactic coronae offers a window into understanding how galaxies evolve over time. The gas in a galaxy's corona is not a static feature. It can be influenced by interactions with neighboring galaxies, mergers, and the influx of material from the broader cosmic web. These interactions can change the rate of star formation, alter the structure of the galaxy, and even lead to the formation of new types of galaxies. For example, when galaxies merge, the hot gas in their coronae can be disrupted, leading to new patterns of gas accretion, star formation, and black hole activity. In the case of elliptical galaxies, these mergers often result in the formation of more massive and quiescent systems, with less ongoing star formation. The gas in their coronae may be heated to such high temperatures that star formation is completely suppressed. On the other hand, interactions between spiral galaxies and their gas can trigger starbursts, where new stars are formed at an accelerated rate. These bursts of star formation are often fueled by the inflow of gas from the surrounding environment, including the cosmic web and neighboring galaxies. Understanding how these processes work, and how they affect the coronae of galaxies, is key to piecing together the overall picture of galactic evolution. The relationship between galactic coronae and the intergalactic medium, IGM, is another area of immense importance. The IGM is the vast, mostly empty space that lies between galaxies, but it is not truly empty. It is filled with diffuse gas, much of it heated to incredibly high temperatures by processes such as the cosmic microwave background radiation. This gas is a source of material for galactic coronae, as galaxies draw in gas from the IGM to fuel their star formation and growth. The interaction between the coronae of galaxies and the IGM is a key factor in understanding how galaxies evolve, and it could hold the key to understanding the large-scale structure of the universe. Recent studies suggest that the gas in the IGM is not as uniform as once thought. Instead, it exhibits complex structures, with dense filaments and voids that connect galaxies across vast distances. These structures, known as the cosmic web, are thought to be the scaffolding that shapes the formation and evolution of galaxies. The gas in the cosmic web flows toward galaxy clusters, where it can be accreted into the coronae of individual galaxies. This process of gas accretion is essential for maintaining the hot gas halos that surround galaxies, and it may be responsible for the ongoing formation of stars and the growth of black holes. Another fascinating aspect of galactic coronae is their potential role in the mysteries of dark matter. Dark matter is thought to make up a significant portion of the mass of galaxies and galaxy clusters, yet it remains invisible and undetectable by traditional means. The distribution of dark matter in galaxies is inferred from its gravitational effects on visible matter, such as stars and gas. One theory is that dark matter may play a direct role in the formation and evolution of galactic coronae. Because dark matter interacts only gravitationally, it does not emit light or radiation, but its presence can influence the distribution and behavior of the hot gas that surrounds galaxies. In this way, the study of galactic coronae may provide clues about the nature of dark matter itself. Researchers are increasingly turning to gravitational lensing as a tool to probe the mass and distribution of dark matter in and around galaxies. Gravitational lensing occurs when the light from a distant object is bent by the gravitational field of a massive object, such as a galaxy or galaxy cluster. By studying how light from background galaxies is distorted as it passes through the gravitational influence of a galaxy's corona, astronomers can map the distribution of dark matter and gas. This technique has already provided valuable insights into the structure of galaxy halos and the role of dark matter in shaping them. While much progress has been made in understanding the role of galactic coronae in the broader context of galaxy formation, there is still much to learn. For one, the exact processes that govern the cooling and heating of gas in these halos remain a mystery. Some scientists have proposed that the hot gas in the corona might be heated by energetic processes like supernovae, or the accretion of material onto supermassive black holes. Other models suggest that magnetic fields might play a crucial role in regulating the flow of gas and preventing it from cooling too quickly. Understanding these processes is essential for unlocking the secrets of galactic coronae and their role in shaping galaxies. The study of galactic coronae also has implications for our understanding of the larger-scale structure of the universe. By studying the gas in the coronae of galaxies, astronomers can gain insight into the processes that govern the formation of galaxy clusters, superclusters, and the cosmic web. These structures are the building blocks of the universe, and their formation is thought to be driven by the flow of gas and dark matter through space. Understanding how gas behaves in the coronae of galaxies can provide key clues to how these larger structures evolve over time. Ultimately, the study of galactic coronae is not just about understanding individual galaxies, but about unraveling the mysteries of the universe itself. The hot gas that surrounds galaxies is a critical component of galaxy formation and evolution, and it plays a fundamental role in shaping the cosmic landscape. By continuing to probe the nature of these invisible halos, scientists may uncover new insights into the nature of dark matter, the evolution of galaxies, and the interconnectedness of the universe. As technology advances and our understanding deepens, the secrets of galactic coronae may one day reveal themselves, offering a glimpse into the inner workings of the cosmos that we have only begun to comprehend. As we continue to delve deeper into the topic of galactic coronae, it becomes apparent that these mysterious halos of hot gas are not just a passive feature of galaxies, but an active participant in their life cycle. One of the most intriguing aspects of galactic coronae is how they interact with other cosmic phenomena. These interactions are not limited to just neighboring galaxies or the surrounding intergalactic medium, IGM. They extend across vast cosmic distances, influencing everything from star formation to the activity of supermassive black holes at the centers of galaxies. In particular, the relationship between galactic coronae and supermassive black holes is an area of intense study. Supermassive black holes, which reside at the heart of nearly every large galaxy, can have a profound impact on their surrounding environments. As matter falls toward these black holes, it heats up and emits vast amounts of radiation. This process, known as accretion, can significantly alter the properties of the hot gas in the corona. In some cases, this radiation can prevent the gas from cooling, effectively halting the formation of new stars. This feedback mechanism is a key factor in regulating the rate of star formation in galaxies, ensuring that galaxies do not produce stars at an unsustainable rate. At the same time, supermassive black holes can also drive the flow of gas in and around a galaxy. The energy released by the black hole during accretion can create powerful outflows of gas, known as AGN feedback. These outflows can affect the gas in the galactic corona by pushing it away or compressing it, altering the structure and density of the hot gas. In some cases, these outflows can even clear out the gas in the galaxy's center, halting the growth of the galaxy and stifling further star formation. Understanding the interaction between galactic coronae and supermassive black holes is crucial for piecing together the overall picture of galaxy evolution. The feedback processes driven by supermassive black holes are not only important for individual galaxies, but can also have broader implications for galaxy clusters. In the dense environments of galaxy clusters, the hot gas in the coronae of individual galaxies can interact with the intracluster medium, ICM, the diffuse gas that fills the space between galaxies in a cluster. These interactions can lead to the transfer of gas from one galaxy to another, and can also influence the thermal structure of the ICM. The feedback from active galactic nuclei, AGN, within galaxies can thus play a role in shaping the entire galaxy cluster, affecting both the individual galaxies and the gas between them. As researchers continue to study the complex interplay between galactic coronae, supermassive black holes, and the larger-scale cosmic structures, they are uncovering new insights into the life cycle of galaxies. One of the more surprising discoveries is that galactic coronae can have a role in galaxy quenching, the process by which galaxies stop forming new stars. While this process was once thought to be the result of gas being used up or expelled from a galaxy, it is now clear that feedback mechanisms from supermassive black holes, as well as the properties of the hot gas in the corona, can play a pivotal role in shutting down star formation. This process of quenching is particularly noticeable in elliptical galaxies, which are often found to be gas-poor and devoid of active star formation. Yet, galactic coronae do not just affect galaxies through these feedback mechanisms. They are also influenced by external factors such as galactic mergers and cosmic inflows. When galaxies merge, the gas in their coronae can be disturbed, leading to dramatic changes in the structure and dynamics of the hot gas. These mergers can trigger new waves of star formation, alter the properties of the supermassive black hole, and create entirely new galaxies in the process. In fact, many of the most massive and brightest galaxies in the universe are thought to have formed through the merging of smaller galaxies, with their hot gas halos playing a key role in this process. The way in which galactic coronae respond to mergers and cosmic inflows is an area of ongoing research. One hypothesis is that the hot gas in these halos may be responsible for regulating the amount of gas available for star formation during these interactions. The gas in the corona can be heated by shocks caused by the merger, preventing it from cooling and condensing into new stars. Alternatively, the influx of gas from the merging galaxies could fuel a burst of star formation, depending on how the gas behaves in the aftermath of the collision. These dynamic processes make galactic coronae central to understanding how galaxies evolve during periods of intense interaction. In addition to these large-scale processes, galactic coronae are also influenced by the smaller-scale phenomena that occur within galaxies themselves. For example, the formation of star clusters within the corona can have a significant impact on the overall structure and dynamics of the gas. As stars form and evolve, they inject energy into the surrounding gas, further heating the corona and influencing its density and distribution. This feedback from stellar populations can enhance or suppress the cooling of the hot gas, depending on the rate of star formation and the types of stars that are being formed. Another important consideration is the magnetic fields that permeate galactic coronae. Magnetic fields are thought to play a crucial role in regulating the flow of gas within galaxies and can even influence the way in which the gas is heated or cooled. In some galaxies, the magnetic fields may be strong enough to prevent the gas from collapsing into new stars, while in others, they may help to channel the gas toward the center of the galaxy, fueling star formation. These magnetic fields are also thought to play a role in the formation of cosmic rays, which can further contribute to the heating of the gas in the corona. The complexity of galactic coronae is compounded by the fact that they are not uniform across all galaxies. The properties of the corona can vary depending on a galaxy's size, age, and evolutionary history. For example, large galaxies with a rich history of star formation tend to have more extensive coronae, with a larger amount of gas and a higher temperature. In contrast, smaller galaxies with less star formation may have less gas in their coronae, and their hot gas halos may be less prominent. This diversity in the properties of galactic coronae makes them a rich field of study, as scientists work to understand how these differences influence the overall evolution of galaxies. In some cases, the gas in the corona may be related to the process of galaxy harassment, when galaxies interact gravitationally with their neighbors, stripping away gas and disrupting the galaxy's structure. This process is thought to be a key factor in the evolution of galaxies in dense environments like galaxy clusters. The loss of gas from the corona during these interactions can lead to a decrease in star formation, resulting in the quenching of the galaxy. This process can happen relatively quickly on cosmic timescales, further emphasizing the importance of galactic coronae in regulating the life cycle of galaxies. As researchers continue to study the role of galactic coronae in the grander scheme of galaxy formation, new discoveries are emerging that challenge our understanding of how galaxies evolve. While much progress has been made in mapping out the structure of these hot gas halos and understanding their interaction with other cosmic components, there is still much to learn. For example, the precise mechanisms behind the cooling of gas in coronae remain unclear. Some researchers suggest that the cooling process may be regulated by turbulence within the gas, while others point to the possible role of magnetic fields or other external forces in controlling the gas's temperature and density. One thing is certain: galactic coronae are not just passive relics of galactic history but are active participants in the ongoing evolution of galaxies. These hot gas halos may hold the key to understanding everything from the formation of new stars to the growth of supermassive black holes. As technology continues to advance and our ability to study these distant objects improves, the mysteries surrounding galactic coronae will undoubtedly continue to captivate astronomers and shed new light on the complex nature of our universe. The significance of galactic coronae in shaping the evolution of galaxies is becoming increasingly apparent, as new observations and models reveal just how much these hot gas halos influence galactic dynamics. One area that has seen substantial progress in recent years is the study of the detailed structure of these coronae. Observations made using advanced space telescopes and ground-based observatories, such as the Chandra X-ray Observatory and the Very Large Telescope, VLT, have provided a wealth of data about the temperature, density, and distribution of gas in the coronae of various galaxies. X-ray observations, in particular, have been crucial for studying galactic coronae. Since the hot gas in these halos can reach temperatures of millions of degrees, it emits X-rays that can be detected by space telescopes. This has allowed astronomers to map the structure of these halos in unprecedented detail. In some cases, these observations have revealed that the gas in the corona is not evenly distributed but instead forms complex, filamentary structures. These filaments may be the result of interactions between the gas and the supermassive black hole at the galaxy's center, or they may be caused by the infall of gas from the surrounding intergalactic medium. The study of galactic coronae also benefits from simulations and models that attempt to recreate the behavior of hot gas in the cosmic environment. These models take into account a range of physical processes, such as hydrodynamics, magnetic fields, and radiation transfer, to predict how the gas in the corona will behave under different conditions. By comparing the results of these models with actual observations, scientists can refine their understanding of the complex interactions that govern the structure and evolution of galactic coronae. This synergy between observation and simulation is a powerful tool in the quest to unlock the mysteries of these enigmatic halos. A particularly exciting development in the study of galactic coronae has been the identification of cold fronts in the gas halos of some galaxies. Cold fronts are regions where cooler gas collides with hotter gas, creating a sharp boundary between the two. These cold fronts can provide valuable information about the history of the galaxy and the dynamics of the gas in the corona. For example, the presence of cold fronts may indicate that the galaxy has undergone a recent merger, with the resulting shockwaves creating disturbances in the gas halo. Alternatively, cold fronts may be associated with feedback from the supermassive black hole, which can push the hot gas outward, causing it to collide with cooler gas in the halo. The discovery of these cold fronts is just one example of how the study of galactic coronae is revealing new insights into the life cycle of galaxies. The dynamics of these halos are complex and multifaceted, with multiple processes occurring simultaneously. As our understanding of these processes deepens, it will allow astronomers to piece together a more complete picture of how galaxies evolve over time. Another aspect of galactic coronae that has garnered attention in recent years is the role they play in regulating the cosmic baryon cycle. Baryons, which are the building blocks of ordinary matter, are distributed throughout the universe in the form of gas, stars, and dark matter. The hot gas in galactic coronae is a key component of the cosmic baryon cycle, as it serves as a reservoir for gas that can either be accreted onto galaxies or ejected into the intergalactic medium. This process is fundamental to the growth of galaxies and the overall structure of the universe. One important question that researchers are trying to answer is how much of the gas in galactic coronae actually ends up being used to form new stars, and how much of it is expelled back into the intergalactic medium. The answer to this question has profound implications for our understanding of galaxy formation and evolution. If most of the gas in the corona is used to form stars, it suggests that galaxies are growing through the accretion of new gas. However, if much of the gas is expelled, it could indicate that feedback mechanisms, such as those driven by supermassive black holes, are playing a dominant role in regulating the amount of gas available for star formation. Recent studies suggest that both processes are likely to be at play, with some galaxies experiencing net accretion of gas, while others are losing gas due to powerful outflows driven by AGN feedback. The balance between these processes is critical for determining the future evolution of galaxies. For example, galaxies that accrete more gas are likely to continue forming stars and growing in size, while those that lose gas may eventually cease star formation and become quenched. This interplay between accretion and feedback is a key factor in determining the types of galaxies that we observe in the universe today. The hot gas in galactic coronae also plays a critical role in the formation of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, consisting of hundreds or even thousands of galaxies, all embedded in a hot, diffuse gas known as the intracluster medium, ICM. The gas in the coronae of individual galaxies interacts with the ICM in complex ways, influencing the overall structure of the cluster. In some cases, the gas from individual galaxies can be stripped away by the pressure of the ICM, while in other cases, it may be heated and compressed by shockwaves within the cluster. These interactions can affect the distribution of galaxies within the cluster and influence the rate of galaxy mergers and interactions. The relationship between galactic coronae and galaxy clusters is an area of active research, as scientists seek to understand how the gas in individual galaxies contributes to the overall dynamics of the cluster. One key question is whether the gas in the coronae of individual galaxies can help to regulate the temperature and density of the ICM. This process, known as cooling flows, occurs when the gas in the cluster cools and condenses, leading to the formation of new stars. The role of galactic coronae in this process is not yet fully understood, but it is thought that the gas from the coronae could provide the necessary cooling for the ICM. Beyond their influence on galaxy clusters, galactic coronae also have important implications for the study of cosmic evolution. The distribution and properties of the hot gas in these halos can provide valuable clues about the early history of the universe. For example, the presence of large amounts of hot gas in the coronae of certain galaxies may indicate that these galaxies formed in the early universe, when the first generations of stars and supermassive black holes were just beginning to take shape. Conversely, galaxies with less prominent coronae may be younger, having formed more recently through the accretion of gas from the surrounding environment. In this way, galactic coronae serve as cosmic time capsules, preserving information about the conditions that existed during the early stages of galaxy formation. As astronomers continue to study these hot gas halos, they will undoubtedly uncover new insights into the processes that shape the universe as we know it. The future of galactic coronae research looks incredibly promising. As technology continues to advance, new tools and instruments will allow astronomers to probe these enigmatic structures in greater detail. For example, upcoming missions like the James Webb Space Telescope, JWST, and the European Space Agency's Athena Observatory are expected to provide unprecedented views of galactic coronae and their interactions with the surrounding cosmic environment. With these new capabilities, scientists will be able to study the properties of galactic coronae in more distant galaxies, shedding light on the processes that govern galaxy evolution across the universe. As we look ahead, the future of galactic coronae research is poised to open up exciting new possibilities. Observations with advanced space telescopes and ground-based instruments will continue to refine our understanding of these mysterious halos and their influence on galactic dynamics. One key area of focus is the way galactic coronae can be linked to the broader cosmic environment, helping to connect the evolution of individual galaxies to the large-scale structure of the universe. One of the most intriguing aspects of galactic coronae is their potential to reveal information about the nature of dark matter. Dark matter, the elusive substance that makes up a significant portion of the universe's mass, is thought to interact primarily through gravity, making it invisible to conventional observational methods. However, the gas in galactic coronae can be used as a probe to study the distribution of dark matter within galaxies. In fact, by examining the way the gas in the corona behaves, scientists can infer the presence of dark matter in the region surrounding the galaxy. This connection between galactic coronae and dark matter is especially important because it may help answer some of the most fundamental questions in astrophysics. For example, how does dark matter influence the formation and evolution of galaxies? Does it play a role in regulating the amount of gas that accretes onto galaxies, or does it affect the dynamics of galactic mergers? By studying the hot gas in galactic coronae, scientists are gaining new insights into the nature of dark matter and its role in shaping the universe. One of the most groundbreaking aspects of this research is the growing ability to detect and measure the elusive gases that surround galaxies. In recent years, scientists have developed new techniques for observing the hot gas in galactic coronae, allowing them to study these structures in unprecedented detail. These observations are helping to uncover the hidden dynamics of galactic halos, revealing the intricate balance between gas inflows, outflows, and feedback mechanisms. For example, high-resolution X-ray observations have enabled astronomers to map the temperature and density of the gas in the coronae of nearby galaxies. By studying how the gas behaves in these halos, researchers can learn about the processes that govern the formation of galaxies and their subsequent evolution. These observations are providing critical insights into how galaxies acquire and lose gas over time, which is a fundamental question in understanding galaxy formation. Furthermore, studies of galactic coronae have also provided new insights into the role of feedback from supermassive black holes. Active galactic nuclei (AGN), the powerful energy sources at the centers of many galaxies, can have a profound effect on the surrounding gas. The radiation and outflows from these black holes can heat the gas in the corona, preventing it from cooling and condensing into new stars. This feedback process is thought to be crucial in regulating the rate of star formation in galaxies, and understanding how it operates within the context of galactic coronae is an important area of research. Another exciting avenue of investigation is the role of magnetic fields in shaping the structure of galactic coronae. Magnetic fields are thought to be present in the hot gas surrounding galaxies, although their precise role remains unclear. Some models suggest that magnetic fields could influence the movement and distribution of gas in the corona, affecting the overall dynamics of the galaxy. For instance, magnetic fields may help to channel gas into certain regions of the halo, or they could inhibit the flow of gas into the galaxy's central regions. Understanding the role of magnetic fields in these processes could reveal important details about how galaxies evolve and how their gas reservoirs are replenished. The study of galactic coronae also has the potential to shed light on the evolution of the intergalactic medium, IgM. The IgM is the vast, diffuse gas that fills the space between galaxies, and it is thought to be the primary reservoir of gas for future galaxy formation. By studying the coronae of galaxies, scientists can gain a better understanding of how gas flows between galaxies and how it contributes to the growth of galaxies over cosmic time. This is particularly important for understanding the process of galaxy assembly, as the interplay between gas infall, star formation, and feedback from AGN will ultimately determine the size and structure of galaxies. Furthermore, recent discoveries have pointed to the existence of very large-scale structures that extend far beyond the visible boundaries of galaxies. These structures may represent the outermost regions of galactic coronae, stretching hundreds of thousands of light-years into intergalactic space. The identification of these extended halos provides an entirely new perspective on how galaxies interact with their environment, and how the gas surrounding them contributes to the overall dynamics of the universe. As observational techniques continue to improve, astronomers will likely uncover even more distant and more complex coronae, revealing further details about the structure and evolution of galaxies. The study of galactic coronae is, in many ways, still in its infancy. There is so much more to learn about the nature of these gas halos, their interactions with galaxies, and their role in the broader cosmic context. The challenges are significant, given the vast distances involved and the faint nature of the emissions from hot gas, but the rewards are immense. By continuing to investigate these elusive and mysterious structures, scientists are unlocking new secrets about the universe and how galaxies evolve. In the coming decades, as new instruments and telescopes come online, the study of galactic coronae will become increasingly important. Instruments like the James Webb Space Telescope, the European Space Agency's Athena Observatory, and the next generation of ground-based observatories will provide new insights into these fascinating cosmic structures. As our ability to observe and model the complex behavior of hot gas and galactic coronae improves, so too will our understanding of the forces that govern the formation and evolution of galaxies. The study of galactic coronae is a burgeoning field that has the potential to transform our understanding of galaxy formation, evolution, and the larger cosmic environment. These mysterious halos of hot gas are more than just a byproduct of galactic evolution. They are active, dynamic structures that play a crucial role in shaping the behavior of galaxies. As we continue to explore the intricate dynamics of these gas halos, we will gain deeper insights into the processes that drive the growth and development of galaxies. Whether through the study of feedback mechanisms, the search for dark matter, or the exploration of large-scale cosmic flows, the mysteries of galactic coronae offer a fascinating glimpse into the hidden workings of the universe. As the field of galactic coronae research progresses, astronomers and physicists are beginning to explore more profound questions about the origins of these gas halos. How did they form in the first place? Were they a necessary feature of galaxy formation, or are they a more recent development in the evolution of galaxies? What role do they play in the broader picture of cosmic evolution? one hypothesis suggests that galactic coronae may have originated from the same processes that led to the formation of galaxies themselves. In the early stages of the universe, after the Big Bang, gas was distributed relatively uniformly across the cosmos. Over time, this gas began to clump together under the influence of gravity, forming the first structures, small galaxies. As these galaxies grew and merged, their hot, ionized gas was expelled into vast halos surrounding them. This process, known as feedback, is thought to be responsible for the creation of many galactic coronae. However, the nature of this feedback is not fully understood. Some theories suggest that the gas in the coronae may be the remnant of primordial material left over from the early universe, captured by galaxies as they formed. Others propose that the gas could have been continuously replenished over time through accretion from the intergalactic medium. In either case, the presence of these hot, diffuse gas halos provides an essential link between galaxies and the surrounding cosmic environment. It is a reminder that galaxies are not isolated systems, but rather part of a much larger, interconnected cosmic web. Beyond their role in the formation of galaxies, galactic coronae may also help us understand the processes that govern galaxy mergers. When two galaxies collide and merge, the interaction between their respective gas halos can have dramatic effects on both galaxies. As the gas in the coronae of the colliding galaxies collides and mixes, it can trigger bursts of star formation, reshape the distribution of gas, and even affect the central supermassive black hole. This dynamic process has the potential to dramatically alter the structure and behavior of galaxies, which makes it a key area of research for scientists trying to understand how galaxies evolve over time. In the context of galaxy mergers, the study of galactic coronae also intersects with research on galactic cannibalism, the process by which a larger galaxy absorbs a smaller one. This phenomenon, in which one galaxy consumes the gas and stars of another, can lead to the formation of a massive, centrally concentrated galaxy with a very large, often disturbed, halo. The impact of such events on the gas in the coronae could provide valuable information about how galaxies grow, and how their gas reservoirs are replenished in these extreme cosmic events. There is also the question of the role of galactic coronae in the broader cosmic cycle of gas. The gas in these halos is not static. It flows in and out of galaxies over time, contributing to the cosmic recycling of material. As gas falls into a galaxy, it fuels star formation and potentially even the growth of the supermassive black hole at the galaxy's center. Over time, this gas is expelled back into the surrounding intergalactic medium, completing a cycle that helps to maintain the balance of matter and energy across the universe. Understanding how galactic coronae fit into this cycle of gas flow is a crucial step toward understanding the evolution of both individual galaxies and the universe as a whole. Interestingly, there are still many unknowns about the precise mechanics of gas flows in and out of galactic coronae. While simulations and observational studies have provided significant insights into the structure and behavior of these gas halos, there is still much to learn about the details of how gas is accreted, expelled, and redistributed across galaxies. For instance, how does gas from the intergalactic medium get pulled into a galaxy's halo? What factors determine whether this gas eventually cools and forms stars, or if it is expelled from the galaxy in a large-scale outflow? How does feedback from stars, supernovae, and supermassive black holes affect the movement of gas in and out of the corona? One of the keys to answering these questions lies in the study of galactic feedback mechanisms. Feedback occurs when the energy and material produced by stars, supernovae, and black holes influence the surrounding gas. For example, when a star explodes in a supernova, it releases enormous amounts of energy into the surrounding gas, which can either push the gas out of the galaxy or heat it to the point where it becomes a more diffuse, hot halo. Similarly, the active galactic nuclei, AGN, in the centers of many galaxies can drive outflows of gas through powerful jets of radiation and particles, affecting the gas in the surrounding corona. Understanding the nature of these feedback processes is crucial for understanding how galaxies evolve over time. Another important aspect of galactic coronae research is the potential role of magnetic fields in shaping the gas dynamics within these halos. Magnetic fields are known to exist in the hot gas surrounding galaxies, but their precise effects are still a subject of ongoing research. Some scientists suggest that magnetic fields could influence the movement of gas within the corona, directing it along specific paths and possibly even contributing to the structure of the gas halo. Magnetic fields may also play a role in regulating the cooling of gas in the corona, which could have significant implications for the formation of stars and the overall evolution of the galaxy. These magnetic fields, while still poorly understood, could help to explain some of the more puzzling observations about galactic coronae. For example, some studies have suggested that the gas in certain halos behaves in ways that are not entirely consistent with traditional models of gas dynamics. Magnetic fields could provide a missing piece of the puzzle, helping to explain why gas in some coronae appears to be confined to specific regions or why the gas behaves in an unexpectedly organized manner. The presence of magnetic fields in galactic coronae is an exciting area of ongoing research, as their role in shaping galactic evolution may be far more significant than previously realized. With advancements in observational technology and computational simulations, the study of galactic coronae is expected to continue to evolve in the coming decades. Future space telescopes, such as the James Webb Space Telescope, will be able to probe the hot gas around galaxies with unprecedented detail, allowing astronomers to map the structure of galactic coronae across a wide range of cosmic environments. Ground-based observatories will also continue to provide valuable data on the dynamics of galaxy halos, as high-resolution imaging and spectroscopy techniques improve. These advances in observational technology, coupled with the growing power of computer simulations, will allow scientists to study galactic coronae in ways that were once thought impossible. By combining data from multiple wavelengths, such as X-rays, optical light, and radio waves, researchers will be able to gain a more complete picture of the complex dynamics of hot gas and galactic halos. These observations will provide critical insights into the forces that govern the formation and evolution of galaxies and their role in the larger cosmic landscape. As we push the boundaries of our understanding of galactic coronae, we may eventually unlock some of the most profound mysteries of the universe. The study of these invisible gas halos has the potential to reshape our understanding of galaxy formation, dark matter, cosmic feedback, and the larger structure of the universe. With each new discovery, we come closer to unveiling the hidden forces that shape the galaxies we observe today and the mysteries that lie beyond them. The secrets of galactic coronae are waiting to be uncovered, and the journey of discovery is just beginning. As our understanding of galactic coronae deepens, the implications for cosmology, astrophysics, and even the very nature of the universe itself become increasingly profound. With each new observation, we uncover more details about the role these gas halos play in shaping the behavior of galaxies and their interaction with the broader cosmic web. While we have made significant strides in understanding these elusive structures, the true extent of their influence on galactic evolution remains a mystery. One of the more exciting aspects of studying galactic coronae is their potential link to dark matter. Dark matter, which makes up about 85% of the mass in the universe, remains one of the biggest unsolved mysteries in astrophysics. Though it cannot be directly observed, scientists infer its presence through its gravitational effects on visible matter. Some researchers speculate that the gas in galactic coronae could be closely tied to dark matter, either as part of the dark matter structure or as a byproduct of its interactions with ordinary matter. The idea of a connection between galactic coronae and dark matter comes from the fact that the gas in these halos behaves in ways that are difficult to explain using only known forms of matter and energy. For example, the density and distribution of gas in the coronae around some galaxies suggests that they are influenced by invisible, non-baryonic matter, potentially dark matter. If dark matter is indeed influencing the behavior of the hot gas in these halos, then studying galactic coronae could provide valuable clues to its properties and role in the universe. One of the challenges of studying the connection between dark matter and galactic coronae is that dark matter does not interact with light in the same way as normal matter. This means that dark matter cannot be observed directly, making it extremely difficult to study. However, scientists have been able to observe the effects of dark matter on the motion of galaxies and the gas within them. In particular, the gravitational influence of dark matter is thought to play a significant role in the formation and maintenance of galactic coronae. The existence of dark matter could help to explain why these halos are so massive and pervasive, yet invisible to conventional telescopes. To explore this further, astrophysicists are developing new techniques to observe the effects of dark matter on the gas and galactic coronae. These techniques include mapping the gravitational lensing of light around galaxies, which can reveal the presence of dark matter. By studying how light from distant objects is bent as it passes through the gravitational field of a galaxy's corona, scientists can infer the distribution of dark matter in and around the galaxy. This could provide crucial insights into the role dark matter plays in shaping the structure of the universe. Beyond dark matter, galactic coronae may also hold the key to understanding the ongoing evolution of galaxies. The gas in these halos is constantly moving, interacting, and changing, which makes it a dynamic and ever-evolving system. Understanding the processes that drive these changes is vital for understanding how galaxies grow and evolve over time. In particular, the cooling and heating processes that occur within the coronae have far-reaching implications for galaxy evolution. As the hot gas in the halo cools, it can condense and fall inward, fueling the formation of new stars and the growth of the supermassive black hole at the galaxy's center. Conversely, when the gas is heated by processes such as supernova explosions or feedback from the central black hole, it can be expelled outward, preventing star formation and potentially even causing the galaxy to shut down. The interplay between cooling and heating within galactic coronae has a direct impact on the life cycle of a galaxy. For example, galaxies with active, hot coronae may experience more star formation, while galaxies with cooler, more quiescent halos may have less star formation or even experience a decline in their star-forming activity. Understanding these processes is key to deciphering the complex history of galaxies and predicting their future evolution. Another area of interest is the relationship between galactic coronae and the intergalactic medium, IgM. The IgM is the vast, diffuse gas that exists between galaxies, and it is thought to be the source of much of the gas that forms galactic halos. The exchange of gas between galaxies and the IgM is an essential part of the cosmic recycling process, and studying this interaction can provide insights into the large-scale flow of matter throughout the universe. As gas flows into a galaxy from the IgM, it becomes part of the galaxy's corona, where it can be heated and enriched by the galaxy's stellar and black hole activity. This gas is then either incorporated into the galaxy's star formation processes or expelled back into the IgM, where it may eventually be recycled into other galaxies. The cycling of gas between galaxies and the IgM is a key element in the ongoing evolution of the universe, and understanding how galactic coronae fit into this process is crucial for understanding the life cycle of matter on the largest scales. In addition to these large-scale processes, galactic coronae may also play a role in the formation of galactic structures, such as galaxy clusters and superclusters. These massive structures are made up of groups of galaxies that are gravitationally bound together, and the gas in the coronae of these galaxies may play a crucial role in their formation and stability. By studying how the gas in galactic coronae interacts with the broader cosmic environment, scientists can gain insights into the processes that give rise to these vast structures. For example, in galaxy clusters, the hot gas in the coronae of individual galaxies may merge to form a larger, more diffuse gas halo that spans the entire cluster. This gas, known as the intracluster medium, ICM, is thought to play a key role in the dynamics of galaxy clusters, influencing their formation, evolution, and behavior. By studying the relationship between galactic coronae and the ICM, scientists can gain a better understanding of how galaxy clusters form and how they evolve over time. As we look to the future of galactic coronae research, it is clear that the study of these gas halos will continue to evolve and expand. With the development of new observational tools, such as the upcoming generation of X-ray telescopes and advanced simulations, astronomers will be able to study galactic coronae with greater detail and precision than ever before. These advances will help to answer some of the most fundamental questions about galaxy formation, the role of dark matter, and the evolution of the universe. Ultimately, the study of galactic coronae is not just about understanding the gas that surrounds galaxies. It is about understanding the very forces that shape the universe itself. These halos are not just passive structures, but active participants in the ongoing cosmic drama. By uncovering the mysteries of galactic coronae, we can learn more about the origins of galaxies, the interactions that drive their evolution, and the fundamental nature of the universe. With each new discovery, we take another step toward answering some of the most profound questions about our place in the cosmos. As we continue to explore the mysteries of galactic coronae, one of the most intriguing aspects that researchers are delving into is their role in the larger cosmic structure. These halos are not isolated phenomena but are deeply interconnected with the fabric of the universe itself. The gas that makes up galactic coronae is part of the larger web of matter that stretches across vast distances. This interconnectedness implies that understanding these halos can unlock secrets about not just individual galaxies, but the very formation of the universe as we know it. One of the most profound implications of galactic coronae is their potential connection to the process of galaxy formation and evolution. These gas halos are thought to play a crucial role in the birth of new galaxies. When galaxies form, they do not do so in isolation. They interact with the surrounding environment, including the intergalactic medium, and the gas in their coronae can significantly impact their growth. As matter falls into a forming galaxy, it is heated to extreme temperatures, contributing to the hot gas that eventually becomes part of the galaxy's corona. This interaction between the galaxy and its surroundings can determine how much matter the galaxy can gather, and how its shape and structure will evolve over time. Moreover, galactic coronae could be seen as a galactic feedback mechanism, one that regulates the growth and development of galaxies. This feedback loop is an essential component of galactic evolution, and understanding how gas is funneled into galaxies and eventually expelled from them could help astronomers understand the cyclical nature of cosmic growth. When gas from the galactic corona is funneled inward, it can cool and eventually form new stars, contributing to the continued evolution of the galaxy. Conversely, when galaxies undergo processes that heat the gas in their coronae, this gas can be driven out into space, preventing further star formation and potentially quenching the galaxy's growth. This interaction creates a delicate balance that has massive implications for how galaxies develop over time. This balance between star formation and the heating or cooling of gas is not just a local event but is influenced by galactic interactions on much larger scales. Galaxies rarely exist in isolation, and many are found in groups or clusters. When galaxies within these clusters interact with each other, the dynamics of their coronae can be altered, sometimes dramatically. For example, when galaxies collide or pass through each other, the gas in their halos can be compressed or heated to extraordinary temperatures. This type of interaction can trigger bursts of star formation or, conversely, prevent further star formation by expelling gas from the galaxy's corona. These processes have long-term consequences, not just for individual galaxies, but for the broader structures in which they reside. The role of galactic coronae in galaxy clusters is particularly significant. Galaxy clusters are among the largest gravitationally bound structures in the universe, and they contain hundreds or even thousands of galaxies. The gas in the coronae of these galaxies does not remain confined to individual galaxies. Instead, it interacts with the intracluster medium, ICM, the vast sea of hot, diffuse gas that fills the space between galaxies within a cluster. This interaction can lead to the exchange of matter between galaxies and the ICM, further fueling the ongoing cycle of gas movement, star formation, and galactic evolution. In some cases, the gas in galactic coronae may even serve as a bridge between galaxies within a cluster. As galaxies move through the ICM, the gas in their coronae can be stripped away, creating a trail of hot gas that links galaxies together. This phenomenon, known as ram pressure stripping, can profoundly affect the galaxies involved. The gas that is stripped from the galaxy's corona is lost to the cluster's intracluster medium, and the galaxy may no longer be able to form new stars, leading to what is known as starvation, or quenching, of the galaxy. The study of this process can help us understand how galaxies evolve within larger structures and how they interact with their surroundings. Interestingly, some galaxies seem to be able to retain their coronae even in the face of these violent interactions. These galaxies, often referred to as resilient galaxies, are able to maintain their gas halos despite the stripping processes that affect other galaxies. This ability to retain their coronae may be related to the strength of their gravitational pull or the nature of their interactions with other galaxies. By studying these resilient galaxies, astronomers hope to uncover more about the factors that determine how galaxies evolve and survive in the harsh environment of a galaxy cluster. Further complicating the picture is the role of magnetic fields within galactic coronae. Magnetic fields, which permeate the space around galaxies, play a key role in shaping the behavior of the gas in the coronae. These fields influence how the gas moves and how it interacts with other galactic components, such as the central black hole or the stars within the galaxy. Magnetic fields can also affect the cooling and heating processes within the corona, either enhancing or suppressing the formation of stars. By understanding the role of magnetic fields in galactic coronae, we can gain a deeper understanding of the forces that govern the dynamics of galaxies. The study of galactic coronae is also shedding light on the larger processes that govern the structure and evolution of the universe. By examining these halos, astronomers are uncovering the processes that control the distribution of matter on cosmic scales. Galaxies are not isolated islands in space. They are part of a vast interconnected network that stretches across the universe. The gas in galactic coronae may provide the missing link that connects galaxies to the larger cosmic web. In this cosmic network, matter is constantly in motion, cycling between galaxies, their coronae, and the intergalactic medium. This movement is driven by the forces of gravity, magnetism, and the ongoing processes of star formation and death. As galaxies interact with each other, their gas halos can be stretched, compressed, and redistributed, affecting not only the galaxies themselves but the larger cosmic environment in which they reside. In recent years, new observational tools have enabled scientists to study galactic coronae in more detail than ever before. X-ray telescopes, in particular, have been invaluable in observing the hot gas in these halos. This gas is typically too diffuse and faint to be detected by optical telescopes, but X-ray telescopes can detect the high-energy radiation emitted by the gas, allowing scientists to map out the extent and temperature of the coronae surrounding galaxies. With the advent of new space telescopes and observatories, such as the James Webb Space Telescope, JWST, the study of galactic coronae will only continue to improve. As technology advances, scientists are also using computer simulations to model the behavior of galactic coronae. These simulations help to predict how gas will behave in different environments, allowing researchers to test their theories and gain new insights into the dynamics of galaxy formation. By combining observational data with these simulations, astronomers are piecing together the puzzle of how galaxies and their coronae evolve over time. Ultimately, the study of galactic coronae offers a unique window into the most fundamental processes in the universe. These gas halos are more than just the hot, invisible envelopes that surround galaxies. They are active participants in the ongoing evolution of the cosmos. They shape the formation of galaxies, influence the growth of stars, and play a crucial role in the large-scale structure of the universe. By continuing to explore these hidden halos of hot gas, we will uncover more about the forces that drive the evolution of galaxies and the universe itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.